We're all ready for it. For your own sakes, I mean, I guess if it makes you feel better. Sorry, this is the alarm company trying to figure things out with them. Yeah, it's not an emergency. They're just they left some equipment at our house and they're trying to get it. So, okay. So we, again, are on the home stretch before spring break. We're going to try to wrap things up here in terms of Ampere's law today. So that way when we get back, we'll be ready to just talk about inductance. I think we'll have a week, maybe 3 class periods when we get back, and then we'll have exam 2, which I know everyone is excited about. So we will try to get that knocked out once we get back. But as far as what we're going to be talking about today, it's all about measuring let's see here, the magnetic field around current-carrying wires. So in this problem, a small current element at the origin has a length of 2 millimeters and carries a current of 2 amps. In the z direction, find the magnitude of the magnetic field due to this current element and indicate its direction on a diagram at each one of these different points here. So the first thing that we're going to want to do is grab our pen here and draw a coordinate grid. So I've got my x and y axes looking something like this. And I'm going to have my current element here. This is going to be the current, and we're going to assume that this current is going to be coming out of the page. So it looks something like this. And P sub A, where we're looking at, is XY. So it's going to be up here and to the right. So 1, 2, and then 1, 2, 3, 4. So we're going to call this P sub A for the point in the first part of the problem. And then the second one is going to be at x equals 2, z equals 4. So P sub B is going to be here above the plane. And what we said last time is that the differential amount of magnetic field contributed by some amount of current is equal to mu naught over 4 pi times I dotted into dl crossed into r hat divided by r squared. And what we also said was this is has a length of 2 millimeters. So this is a finite length wire. And we said last time that the magnetic field, B, is equal to mu naught over 4 pi times I over R times sine theta 2 minus sine theta 1. And bear in mind that the front of this wire is 1 millimeter above the plane. And the back is 1 millimeter behind the plane. Now, looking at just this center cross section of the wire, we want to look at here what this radius r is. Call it little r sub a. Where r sub a, Actually, let's say this first. The first piece of this puzzle, if we're looking at this formulation right here, we need to consider that dl is equal to dl in the k direction. And we also want to consider, too, we've also got to consider, too, that r sub a is equal to 2I plus 4j, at least as far as that little cross-section is right there. And r sub a hat is equal to r sub a divided by its magnitude, so 2I hat plus 4j hat divided by the square root of 20. And it's also worth noting, too, that r sub a squared, then, is going to be equal to 20 meters. Everybody with me so far, other than ready for spring break? All right. Then, what we want to consider here, and you likely won't have a problem like this, certainly not on the exam, but I want to talk you through something here, is that since L is so much smaller than R, then we can approximate we want to approximate dl is just going to go to some delta L, the total length here. What I'm trying to say is, if you were to do the integral here of dl cross r, think about it that r is the square root of 20, so over 4 meters away, 4.5 meters away, roughly. And then we're integrating over this segment of wire that is 2 millimeters in length. And so we're looking at how that angle of the sine thetas up there, sine theta 2, sine theta 1, how that's going to change if I'm looking at 1 millimeter separation, right? If you look at the about double the width of my fingernail, at least as far as where you're sitting from your own spots, from the top of my fingernail, the top of my finger, to the underside of my fingernail, you really can't tell that there's any change in angle between those two points, right? So that's the assumption that we're making here, is we're instead of doing this integral, because the angles are changing so, by such a tiny fragment from the top of the wire to the front of the wire to the back of the wire, instead of doing the integral, we're just going to do this as a product instead. Do y'all catch my reasoning there? Okay. So, in this case, for part A, we get that B is equal to mu naught over 4 pi times I delta L, which is in the k hat direction still, crossed into r hat, all divided by r squared. And so we get that we know what I is. What we want to look at is that this is, let's take everything that's not a vector out here. We get mu naught I delta L over 4 pi r squared times k hat crossed into, that would be r sub a squared, crossed into k hat, or k hat crossed into 2I hat plus 4j hat. but I'm missing something here. I also need to consider, too, that I have an extra term of r sub a that would be underneath this from this term right here. This is r sub a. So I would actually have to change that to r sub a cubed. So plugging in what we've got here, let's look at that. This would be 4 pi times 10 to the minus 7 times the current of 2 amps times the length of 0.002 meters, all divided by 4 pi. R sub a is the square root of 20. So this is going to be 20 times raised to the power 3 halves. And now we want to consider what k dotted into, or crossed into I is, and k crossed into j is. So what is k crossed into I? J, exactly. So I'm going to have 2j, and then k crossed into j is minus I hat, so that's minus 4 I hat here. Or, if you multiply everything out, this comes out to be minus 1.79 times 10 to the minus 11 Tesla in I hat, plus 8.94 times 10 to the minus 12 J hat, and again, this is all in Tesla. The Earth's magnetic field is on the order of 10 to the minus 5, 10 to the minus 4 Tesla. So this is an incredibly weak magnetic field. Yes?
I'm just kind of confused how you went from, how did you get the first equation in part A? Like where?
We ended up because...
R squared.
The r squared term right here?
Yeah, because you go from dB to just B.
Oh, remember, this is the formula or the equation that we derived for finite length right here. And we ended up not using it, considering that the angles changed so insignificantly here. It would have been hard. I mean, you could have figured out what sine theta 2 and sine theta 1 were. You would have had to find the angle between, if I could draw it out, if this is the back of the wire, and this is the front of the wire right here, right? Yeah. Imagine that this is only 2 millimeters. And up here, somewhere well above it, so I'm looking at this point right here, which is a distance r sub a equals square root of 20 meters away, right? This distance right here. So the angles that I would need to look for are going to be this angle right here. I'm trying to think of I think it would be from, depending on how we derived it. I can't remember on this one. Let's see. Sine theta, you'd want it to be greatest at pi over 2. So yeah, it would be from theta 1 right here. And then this angle right here is going to be theta 2. So you could calculate what those are. We didn't end up using this solution right here. I just turns out it was less work to go back to this differential, and you're wondering, okay, why did we get from, okay, so how did we go from dB to B right here? Okay, I'm sorry. The integral that we're doing, we'd have to integrate over both of these. And what I argued was that all of these terms right here, even this cross product right here, is changing very little over the course of the integral, right? Because this angle changes by such a small amount right here, right? And with that, the only thing that is changing here then, because we're integrating over L, is just the length itself. And so I did the integral, and I just said that the integral is just the same as if we just took the length in and substituted it in anyway. So I did do the integral. I was expecting the integrand to change very little. So if the integrand changes very little, it's constant with respect to the integrating variable. And if that's true, we could pull everything else out right here, out of the integral. And then what's left over? If you consider your limits of integration would be from minus L over 2 to L over 2, right, if we're integrating in z. Well, then you end up getting L over 2 minus negative L over 2. That comes out to be the length of the wire right there. Does that answer your question? Okay. I can put the QR code back up. Any other questions on this one? The 20? Okay, that's a good question. Where did square root of 20 come from? Well, if we know that r is 2i hat plus 4j hat, right? Then r is going to be the magnitude of that vector. So that's the square root of 2 squared plus 4 squared. Does anybody want to take a stab as to what part B, the answer to part B would be? Same thing with different components? Almost. Yeah. I mean, what changed here, right? I mean, we brought it down onto the x-axis. So it means we have no component of y in our radius r sub b, right? But then we do add a component r sub z, or r bz. You wouldn't consider the z component because we'd be crossing into dl, which is in the k direction. And so the only thing that survives is this j term right here, because the j term came from crossing k into I hat, and I hat doesn't change, and so the answer ends up being 8.94 times 10 to the minus 12 j hat Tesla. That's it. So yeah. Why does the z component go away? Okay, the only thing that would change here in terms of what we have derived so far in this equation is instead this would become for k hat, because we went from x equals 2 to y equals 4 and z equals 0. And we just switched basically the 4 was on the y, now it's on the z. So k crossed into k is 0. So the only term that survives is k crossed into 2i, which is our j component of this term down here. So, boom. Roasted. No, just kidding. Okay, that's a good question. So we have the term of r squared right here, right? But then I had to consider that there's an r hat right here. R hat is equal to r vector over the magnitude of r. So I went and I've got r, the vector, up top here. So this component in the square brackets is r. So I had to divide by another factor of magnitude r here. So the last thing it says is indicate the direction on the diagram. So help me indicate the direction on the diagram either from your right-hand rule or from the components of the vector given to us. So I reach out here, I would stick my thumb coming out of the page, and I want to reach towards the point A. So thumb's coming out of the screen, I reach my fingers up there, and then my palm points in the direction of the magnetic field, which would be up and to the left. So I've got B should look something like this from using the right-hand rule. And you ask yourself, does that make sense in terms of what we calculated? Well, yeah, we said we should have a negative 10 to the minus 11 component in I. So negative in I would be back to the left. And then a positive J component, that would be up. So this is left and up. And we have that our X component is going to be slightly larger than our Y component, just by not even double that value. Or I guess right at double that value. So yeah, this is going to be laying over to the left a little bit more than it is pointed up. What about this point right here? In what direction is the magnetic field at point B? Again, align your thumb to the direction of your current. The current's coming out of the screen. Reach to the right to grab the point P. Your palm points up, which is exactly what is said right here for our answer to part B. So the magnetic field here is going to look like so. Mu naught, the definition of mu naught is equal to 4 pi times 10 to the minus 7. And I don't remember what the units are of that right now. It's permeability of free space. It's like Tesla per meter squared time per amp meter squared or something like that. So in this problem, it does vary ever so slightly, you're right. But the net result at that point, you would have to have the points that are going to be bent to the right or into the board and out of the board after you integrate over that hole, those would cancel out. But you're right, if you just looked at the segment at the back, there would be an additional component. But when you consider the whole segment, those back into the board and out of the board components end up canceling out. Okay, let's do one that's a little bit easier. A single conducting loop has a radius equal to 3 centimeters and carries a current equal to 2.6 amps. What is the magnitude of the magnetic field on the line through the center of the loop? And perpendicular to the plane of the loop, A at the center, 1 centimeter from the center, 2 centimeter from the center, and 35 centimeter from the center. So our loop, our current loop, is just going to look something like this, where we've got our current I. Let's allow it to go around in this direction. We'll say counterclockwise. And our radius, this is going to be R right here. We'll call this big R. And one of the things that we derived last time is when we're looking at the center of the current loop, we said that the magnetic field at the center of the current loop is equal to, and let's just look at the magnitude right now, is equal to mu naught over 2 times I over R. So that's 4 pi epsilon, 4 pi times 10 to the minus 7 divided by 2 times the current I of 2.6 amps over the radius of 0.03 meters. This comes out to be 54.5 microtesla. We're much closer to the wire, which is where we see the biggest gain in magnetic field strength, and the fact that this is looped in on itself, all parts are equally close, so we get an increase there as well in terms of our magnetic field strength at the center. Now let me ask you this. Is the magnetic field, well, in what direction is the magnetic field at the center of that loop pointed? It's going to be out of the board. Yes, you're right. If you look at the bottom of the current loop, the current's going to the right. I reach up to the point at the center. My palm points outward, so the magnetic field is going to be out of the screen. In fact, if you look anywhere inside this current loop, the net result is going to be that the magnetic field is going to be out of the screen. So this is what the magnetic field is going to look like inside the current loop. Like so. And you could play with the right-hand rule to convince yourself that that's true. Now, what about areas that are outside of the current loop, at least in the plane here? In or out of the current, in or out of the screen? Well, it's going to be into the screen at that point. I mean, you could think about that by doing your right-hand rule, or you could consider that current magnetic fields have to make closed loops, right? And if magnetic fields make closed loops, if it's coming out of the screen somewhere, it has to be going back into the screen somewhere else. And as we look at the point that is in the center of the circle, but raised out of the screen a little bit, which is what's being asked here, 1 centimeter above the center, 2 centimeter from the center, and 3 centimeter. It always says, what is the magnetic field on the line through the center of the loop. So now we're going to look at 1 centimeter from the board, out from the board, 3 centimeters out from the board, and then 35 centimeters out from the board. In every case, the magnetic field is still going to be pointed out towards you guys. If you do that cross product in the right-hand rule.
How would you do the right-hand rule
For the ones that are into the screen? So now let's look at I, and I'm going to focus on this point right here, right? So I'm looking at I at the bottom of the loop, so I've got to align my thumb to the current, which is going to the right, and then I reach down to that point. My palm points into the screen now. And the net result of all of those, I mean, if you think about it now, if you do that same logic, look at the top of the screen. The current's going to the left, but I reach down, but the magnetic field is out of the board. So at this point, let's call it P, the magnetic field from this point of current loop is out of the screen. But up here from this one, if I look at this point, the magnetic field is into the screen. But how did I determine that the net result was going to be a magnetic field that was into the screen there? How did I determine that the net result was out of the screen if I found that at one place, or from one part of the current loop, the magnetic field was into the screen, and from another part of the current loop, it was out of the screen? Yeah, the bottom of the loop is closer, right? We said that magnetic field strength goes as R hat over R squared, right? I mean, that was in our Biot-Savart law, right? Well, that means that as I get further and further away from a line of current, then the magnetic field strength is going to diminish. So this would be very strong right here due to the bottom of the current loop, and this would be very weak. So the net result is a strong outward component. I think I've got those backwards, don't I? That would be into the screen, and this would be out of the screen. I've got a strong inward component, but a weak outward component. The net result is going to be into the screen. You can do some cool things with programming and actually show these loops around the wire if you wanted to.
So you're saying it's going to be stronger because you're reducing the radius that it's going from the center or from...
No. So this is the distance. R is from where you're measuring the current, or from the current itself, to the field point. And so for this one, the distance from the current to the field point is very small in comparison to this one where the radius from the field point, or from the current to the field point is very large. Yep. Part B, when we're above the center of the loop, we said that the magnetic field is equal to, the magnetic field strength is equal to mu naught over 2 times R squared times I over Z squared plus R squared raised to the 3 halves, where in this case, Z is equal to 0.01 meter, and you would end up getting 46.5 microtesla. In part C, you would get 31.4 microtesla, and at D, you would get 34.3 nanotesla. Yeah, for C and D, you use the same equation because we're still looking along that line on the center axis. The only thing that changed was here Z is equal to 0.01 meter. Here Z is equal to 0.02 meter. And here Z is equal to 0.35 meter. Okay, so the question was, why did you use a different equation for part A and part B? Does anybody remember what the difference between these two equations is? Henry? There's additional components to the radius that we're looking at here that we're considering in part B. Is what it comes down to. What would be a good exercise is convince yourself that these two equations are the same when Z is equal to 0. Right?
Oh, it is, yeah.
Yeah, it's the same. When you're in the center of the loop, Z is 0. Jacob? For what part? For the center of the circle? So choose any point on that current loop and then reach towards the center of the circle. Yeah, with your right hand, not your left hand. Your left hand will fail you every time. Yeah, so on the bottom of the current loop, I'm going to the right and I reach up towards the center, my palm points out. If I go to the right side of the loop, the current's going up along with my thumb, but I reach to the left, it's still coming out of the screen. No matter where you look all the way around that loop, it's coming out of the screen.
So X's are into the screen.
X's are into the screen, dots are out of the screen. Remember, if you see that notation, the dots, you're seeing the point of the vector arrow coming towards you. If you're seeing the X's, you're seeing the fletching on the back of the vector going away from you. Okay, let's do at least one more here, and then we'll switch to new stuff and just trying to read the room, maybe get out a little bit early. What's up, Andrew? Yeah, I mean, you'd have to consider, let's again keep playing with this point down here at the bottom of the screen. You would have to consider this point, and this point, and this point, and this point, and those are all going to give some amount of leftward, or for this one right here, it would have to give some sort of rightward component, but those are all going to cancel out the leftward and rightward components, and the net result is going to be just into the screen here. You could think of this is coming out of the screen right here and then goes into the screen and then kind of loops around like so. All right. If currents are in the negative x direction, so going to the left here, find the magnetic field at the following points on the y-axis. The y equals minus 3, y equals 0, and y equals plus 3, and y equals 9. So what I'm going to do instead is redraw this according to a couple different configurations. The first one would be, let's look at the y projection, or yz projection, I should say, yz, in which case I have, let's see, y crossed into z, x would be out of the page. Out of the page, not into the page. And that means that one of my lines of current looks like this, and the other one looks like this. And P sub A then is going to be here. P sub B is going to look like so. P sub C like this. And then the point P sub D would be somewhere out here. So part A, we said for an infinite line of current, which as far as we can guess, since it doesn't give us length, then we just got a cutout here. This is an infinite line of current, that the magnetic field magnitude is equal to mu naught I over 2 pi times the distance from the wire to the field point, R. And what I want to do is I'm going to call this wire 1 and wire 2 respectively, such that if we look at part A, R1 is going to be like so, and R2 like this. So looking at wire 1 and point A, in what direction is the magnetic field due to wire 1 at point A? Up, down, left, right, into the screen, out of the screen, looking at this projection right here, the YZ projection. So in what direction is the magnetic field due to wire 1 at point A? Would it be down? So it's going to go into the screen. I reach out to the point. Yes. The magnetic field due to wire 1, so let's call this BA1, is going to be down. Now what about from the current on the right, wire 2, at point A? In what direction is the magnetic field for that one? It's going to be up, and it's going to be in lesser magnitude because it's further away. So this would be BA2. And the net result is that the magnetic field at that point is going to be equal to BA2 minus BA1 K hat. Just based on the geometry, one is going in the positive K hat direction, that's BA2, and then BA1 is going in the negative K hat direction. Right, so the direction for magnetic field, taking wire 1, the wire on the left, align your thumb in the direction of the current that's going into the screen, right? And then I reach out to the right to the point P sub A. My palm points down then, or my fingers curl in the downward direction. So that's how I get BA1 is down in the negative K direction. So now we know that the magnitude here, we're going to substitute this in to each one of these two values. So I get mu naught I over 2 pi R1, R2, minus mu naught I over 2 pi R1 K hat. And we can even pull out all of the terms because it's the same current. Both have 20 amps each. They don't tell you that in the problem. That was a typo on their part. But each has 20 amps. So that means I've got mu naught is a constant. I can pull that out. They have the same current. I is 20 amps. We can pull that out. 2 pi is a constant. We can pull that out. So we're just left with 1 over R2 minus 1 over R1 K hat. And the net result is minus 8.89 times 10 to the minus 5 Tesla in K hat. So what's the answer to part B? What is the magnetic field in the midpoint between these two wires? It's 0, yes. If you reach out from wire 1 to the right, you still get a magnetic field that's down. If you reach out to the left from wire 2, you still get a magnetic field that's up. They're same current, same distance at this point from each of the two wires. So yes, you get that the magnetic field strength is 0 here in the middle of the two wires. What about at point C? It's going to be the same as part A, but now it's going to be going up. Yes, you've got the exact same scenario, but now the upward facing BC2 is so big and BC1 is so big. And so, yeah, you get plus 8.89 times 10 to the minus 5 Tesla in K hat. And part D, you can check for yourselves on either my solutions or do it yourself, but you get minus 1.6 times 10 to the minus 4 Tesla. Yeah, so for part D, both are going to be pointing down. Exactly. Yes, good. Andrew? X's mean going in. But it says the currents go in the negative X direction, right? So yes, Y crossed into Z tells me that plus X is out of the screen, and since the currents are going in the negative X, they go into the screen. Oh, I've got it drawn, I see. I've got it drawn incorrectly here. Yeah, if the currents were reversed here, then all of the directions that we've drawn would have been reversed, and this would have been positive, this would have been negative, and this would have been positive. On at least one problem, you will have where the direction matters, the positive or negative will matter, yes. Not on all of them, because I don't want you to lose points every time, but yes, on at least one of them. And you can probably guess, too, that there's going to be a conceptual question where the correct answer is minus k or something like that, and I also give you plus k, just directions. You will get partial if the answer is positive and you guess negative. Most of the time, I credit that as 3 out of 4 points on a numerical problem. I asked this question, I think, to you guys if you took me last semester and to my Phys 2 last semester, and the general rule of thumb is, who has time to go anywhere but a place to study? And I thought, okay, that's fair, I guess. Yeah, and that was another thing, too, where there were several students who had no idea what some of these places were, which kind of caught me off guard. Y'all got to get out more or something, I don't know. Easier said than done when you're a science or engineering major. This also made me think, I think it was last time where it was, what's your favorite study food? And it was Frodo saying, I don't remember the taste of water. And that, like he also, I feel like this could be too, I don't remember the grass under my feet and whatever the rest of that monologue is as he's contemplating death at the edge of Mount Doom. Yeah, what's grass? My colleague at Harding had a sign on his door, and it was just like Jeff Foxworthy, you might be a redneck if, but it was you might be a physics major if, which I think works for most of the majors in these buildings here. It's you might be a physics major if you don't remember what's behind the door that says exit, which is true. Kind of get caught up in there. Okay. So the last thing that we're going to talk about before we wrap up, before spring break, is Ampere's law. Ampere's law is one of the 4 Maxwell equations if you take electromagnetic theory. And it's what we're going to show is the more or less magnetic equivalent to Gauss's law for electricity. We said that Gauss's law states what? Somebody help us remember, what does Gauss's law state? Gauss's law was not about current, it was just about, so charge was related to flux, right? You have some closed container here. If I put a positive charge inside my water bottle here, then the amount of electric field lines coming through the surface of my water bottle is proportional to how much charge is inside of it. So Ampere's law says something very similar. If you have a loop instead, and there is current that goes through the loop, then the net sum, or the net integral of the magnetic field around that loop is proportional to how much current passes through the loop. So Gauss's law states that for a closed surface, net flux is proportional to the source charge. For this one, Ampere's law is similar in that the total magnetic field around a closed loop is proportional to the current passing through the loop. Or that is to say that B, the integral of B around this loop right here, is equal to mu naught times I, where I sub c is the current that passes through the contour C on the diagram. And if you know the length of your perimeter of the object that you're dealing with, for a circle, it's 2 pi r, right? Or pi times the diameter, 2 pi times the radius. And you know, based on symmetry, that the magnetic field is constant around that loop, or its strength is constant, its direction is going to change, then this is going to make for an easy way for us to calculate what the magnetic field is using Ampere's law, instead of having to use the Biot-Savart law. Yes?
I know I asked this last time, but what does the little circle around the integral mean again?
Oh, that means a contour integral. So without that circle, it just means you're integrating over some path. The circle on the integral means that you're integrating on some path that comes back to its starting point. So say you start your integral up here at the top of the loop. It means that you're going to go all the way around and you end back up.
So you basically evaluated the same.
Yeah.
Okay.
Yeah, it's evaluated the same. It's just a notation for one that closes in on itself. So you can use this according to the solution above, where based off of the Biot-Savart law, I know that the current's not changing. I know that the distance isn't changing. So I expect for constant distance from the wire, the magnetic field strength is constant. And so taking the integral around, the magnetic field strength is constant. It gets pulled out to the right of the or to the left of the integral. So then I'm just integrating around dl, which is the perimeter of the circle, 2 pi r. Mu naught I does not change. So we calculate that the magnetic field around that infinite wire is mu naught I over 2 pi r times phi hat, where phi hat is going to be in the direction of, if you consider in cylindrical coordinates, let's let z be the direction going from left to right here, and r be the distance away from the z-axis. Then maybe the easiest way to say it is, I'll draw this out in a second on the screen. But just like you've got I, J, and K in Cartesian coordinates, you've got r, phi, and z in cylindrical components. So phi is the direction that is perpendicular to the current and the radius that you're looking out to, which is what we said already with Biot-Savart law. Yes? The C denotes the current that passes through the contour, that pierces the contour, or the plane bounded by the contour. So if you're doing Ampere's law for a long straight wire, where the current density is uniform in that wire, so the current isn't all on the outer shell there, you've got the current is uniformly distributed across the cross section here. Just like we did with Gauss's law, when the charge was uniformly distributed through, say, the sphere, we get that inside of the loop, the magnetic field strength, or inside the wire, the magnetic field strength is going to increase linearly with distance. Conceptually, what you can think of is the contour that you're dividing by, the perimeter, only increases as a function of r, but the area enclosed increases, which is the area enclosed is going to enclose more current. The area goes as r squared. So we get an increase in magnetic field strength as you go from the center of the wire to the outer edge of the wire. And then once you leave the wire, the magnetic field strength is going to drop off as 1 over R again.
So are we saying that there's only current inside of little r?
No, we're saying that there is this total current I is going to be uniformly distributed over the whole copper-looking section here.
So why is there a difference between when we're inside that circle and outside that circle?
It's not about what's inside or outside the circle. The circle could be anywhere from as small as, infinitesimally small here, all the way out to the outer wall. But either way, we're increasing the amount of current within this loop as we increase the radius of that orange loop.
It's saying outside the whole wire.
Yeah, this is outside the whole wire. This is outside the whole wire here. And so you get something that looks something like this right here, where the current is, magnetic field is going to increase linearly with radius until you leave the wire, and it's going to drop off as 1 over R. Inside of a toroid is just like the solenoid that we talked about last time, but where you take the ends of that solenoid and you wrap them around on themselves, making a closed loop. Well, if you look at, say, the dashed line being inside both walls of the toroid, then I enclose 0 current. And by enclosing 0 current, I expect there to be no magnetic field within both walls of the toroid. But then as I cross through one of the walls, you can see that right here, I get that the current is going to pass through the contour, and then it's going to loop underneath and come back over the top, and it's going to pass through again and again and again and again. And so what ends up happening is that the magnetic field strength is equal to the total number of turns of the current around the toroid times mu naught I over 2 pi, where now little r does not denote the distance from the wires. Mu naught r, little r, denotes the distance from the center of the toroid. And so in this case, you would end up getting a magnetic field that is going around the inside of this toroid in the clockwise direction. It's actually a convenient way to make, for example, particle accelerators. Right? If you can increase the accelerating potential by some mechanism along the walls of, or in this direction, and consequently also increase the current going through this wire, then you increase the magnetic field strength, and so you can keep a charged particle locked in on that magnetic field and increase its speed over and over and over again, or at least as long as you have enough energy to do so. N is the number of times that the current wire, or the current of wire of current is passing around the toroid. Yes. So magnetic field strength always changes as a function of inverse distance. True, false, or something else. How many of y'all wish that Tralse was an answer on your exam sometimes? I know I always did. All right, this is false. A couple of counterpoints to that. Remember when we were inside of the wire, it increased linearly with distance from the center of the wire. If you think of a solenoid, a long straight solenoid, we said that the magnetic field was constant inside of the solenoid, so that didn't increase with distance from the wire. So just a couple of counterpoints there. Another question. Which of the following statements is true about the application of Ampere's law? All right, so none of these statements are correct. If you look at the first statement, Ampere's law can only be applied if the current distribution is uniform. That's false because Ampere's law is always true. But what maybe if you answered that one, you were thinking is that Ampere's law is only useful for calculating B if there's symmetry invoked. That we need a symmetrical contour to make it useful to us to calculate the magnetic field. The second one was false because Ampere's law is true for any closed loop. And Ampere's law cannot be used when there's no current enclosed. That's false. It just means that the magnetic field is zero if there's no current enclosed. Okay, last thing, and then we'll wrap up here. Magnetization. Just like when you embed an object into an external electric field, the molecules inside of that material got polarized. By the same discussion, you can embed some kind of material inside of an external magnetic field, and you can therefore magnetize the material. So by putting a material inside of an external magnetic field, you can magnetize that material. And what is going to happen is that the net magnetic field inside of the material is going to be equal to the external magnetic field plus mu naught times the magnetization. And the magnetization is defined as how much of a magnetic moment you have in an increasingly smaller volume. And what we get is just like we had for polarization, a lot of materials in many regimes behave linearly with the external magnetic field. So as external magnetic field increases, you expect that the magnetization of the material to increase linearly with that increase of the external field. And so we get again that the magnetic field inside of the material is going to be equal to the magnetic field outside of the material times 1 plus chi sub m. Chi sub m, I've forgotten what that one's called. Kappa sub m is going to be the relative permeability of the material. Chi sub m is called, I haven't taught this in a year. I haven't had to think of it. The magnetic susceptibility of the material. Chi sub m is the magnetic susceptibility of the material. And so if you want to know what the permeability of the material is, you take kappa sub m and multiply it by mu naught, the permeability of free space, which I don't think I have written down here. All right. We'll do magnetic moments of particles later because we're not going to really end up using that. I would recommend if you have any fascination whatsoever with your material, paramagnetism, diamagnetism, ferromagnetism, finding the difference between those. If you want to save these links on your device for later, these are the 4 videos that I said are really cool in terms of understanding why there's that weird cross product in magnetic fields. And the last thing is questions. If you don't have questions, you can go, or if you don't want to stick around, you can go. Jacob, what's your question?
Videos, are they available, like, if you go to, like, the slides that you post, are they there?
I have not updated my slides, but I'll make sure they get updated tomorrow. Yep. What? Manatee? Wait. Magnetism? Oh yeah, it's really weird, fascinating stuff. Spring break plans. I'm going to work on a garden. Can we push the homework due tonight back a day or two? I for one am traveling home for spring break tonight. Yeah, I really don't mind. I just didn't want it to be due after spring break. So yes, I'm fine pushing the homework back. I'm anointing you to send me a message to remind me. Yes, we'll push the homework back a day or two. Yep. You too. See you later. Bye. So if you look, so remember, it depends on distance, right? The magnetic field strength depends on distance. The further you are away from something, the weaker the field gets. So I am closer to this wire, which gave me the downward facing magnetic field. So it's going, I just chose some distance for that. But then I'm further away from this wire, which has an upward component. I know it has to be lesser in magnitude because I'm further away.